record it, but then you listen, and then you get the job, and you get legislation. I'm very relaxed. Last week,
well, good evening, ladies and gentlemen, and thank you for coming this evening. This is our first talk of the session, and it is something different. But I've just sent to Bob, our speaker. Stop here. Good evening, ladies and gentlemen. Thank you very much indeed for coming along this evening. This is our first talk of the session, and it is something different. A lot of the concentration of what we've been doing in the past has been, not all of it, but the vast majority has been into metallurgy and mechanical engineering and structures and things like that. But the history of technology and engineering is far, far broader than that. And I'm delighted that Bob is coming along to give us a talk on the high-frequency transceivers. Just a few, sorry, I'll pass over to John to give out the programme. And then Felix, I'm just going to say a few words.
Okay, thanks everybody online. Any problems with the sound or anything, let us know. As usual, the IT setup here has been tweaked, as has Zoom, etc. We think it's all working okay, but any problems, give me a shout. But do turn your volumes on your computers up, please. Programme for this time round, very quickly. Next meeting is in October when we have new maps from hell. Phil Judkin running through the first use of naval drones. It's much earlier than you think. We're right back to the First World War. What I'll do is I'll take the rest of the programme at the end. Pass this on to Felix.
Thank you. Delighted to welcome Felix Smith to the meeting tonight. Felix is the current president of the Newcomen Society, and he's going to say a few words.
Yes, thank you very much. I'm delighted to be here. It was a bit of a challenge to come here because I had to go via London and Doncaster, but hey, we try, starting in Manchester this morning. Anyway, I'm delighted to be here, and particularly because it's electronics, or, well, electrical engineering. It's sort of mixture, and it's also fairly recent. I always say the topic of interest of the Newcomen Society starts yesterday and goes back. It's not something which is got to be 300 years old or 1,000 years old. If it's a day old, it's already history. So we can quite live with that. And as I said, because I'm originally an electrical engineer, and very pleased to see something on electrical waves, or electromagnetic waves rather. So the other point I was hoping to make was, how many people here are members of the Newcomen Society? If you're not, then this doesn't mean that you have to pay, but you're encouraged to join the society. It's a very good society. It produces 2 magazines. It produces a sort of less technical magazine called Links, and it also produces the International Journal for the History of Engineering and Technology. And you're not just invited to join the society, but of course, we always look for papers and articles for those 2 journals. So if you feel lighthearted and you'd like to write something of about 500 to 1,000 words, Links is your destination. If you're feeling like something really tough and hard, for example, on HF, which you can't see, which you can't touch, but they're there, then the International Journal is probably the voice which you will be using. So if you have any questions or queries at the end of this session, I'm very happy to answer. We have a council meeting next Thursday, so if there's any issues that you would like me to take to the council meeting, also just let me know. No tomatoes, please.
Thank you, Felix. Thank you. Felix just mentioned the journals that the Newcomen Society produce and the magazine. I brought a lot of older magazines there that people might like to have a look at. And I think they go back to 2009, 2008. So please feel free to take either 1 or 2 or 3 of those magazines at the back. I'm delighted to welcome Bob Harris to our talk, to give us a talk this evening. Bob and I worked together at Sheffield Hallam University for a large number of years. So I've known Bob for over 30 odd years. Bob's had an amateur radio license since 1971 and has gradually built up a collection of old radio transceivers. What I mentioned to Bob, old transceivers, he said, what do you mean by old? And he's right. The date on there is 73 to 86. But I think it starts at the oldest to the relatively new one at 86. These are from the mid-1970s until the mid-1980s, these radios. This period being one of the significant technical change and innovation. Professionally, Bob was a Master of Science in Modern Electronics and a Bachelor of Engineering in Electronics Engineering. After initially working in the steel industry, he moved into teaching in further education. Laterally, he taught electronics and telecommunications at Sheffield Hallam University until his retirement. So welcome, Bob, and thank you for agreeing to give a talk this evening.
Thank you very much, David. Good evening, everyone. I'm conscious there's a significant number of people online, so please forgive me if I start doing things in the room that you can't see. I'll try and avoid doing that, but it might happen. Okay, let's give a bit of a starting point. I've ended up, not particularly because I intended to, collecting old radios. The sort of 73 to 86 being an example, but they go a little bit later than that as well. And that led to my writing an article for the Radio Society of Great Britain's magazine, which is the development of HF transceiver. I should say, and I'm sorry, this is where I need to be more careful. HF, for HF, it means shortwave. Okay, that probably gives you an immediate appreciation of what we're talking about here. Having written the article which was published, it was then sort of seemed reasonably possible to turn it into a talk. So that's where we are at the moment. And I'm sorry if you're online, but I'm just going to show the people in the room here. This is going to be the sort of the starting point. This is an American Atlas 180 from 1973. So that will be technically our sort of starting point. And I'll talk more about it as we go on. And then we're sort of ending up with this, which is I can hardly hold it with one hand, which is a Japanese radio. Overtly, they do the same thing. They allow voice communications on shortwave. However, you might say a Model T Ford and a current electric, EV, electric vehicle do the same thing. Well, they sort of do, but they're completely different. So that's sort of the way I'm coming at this. So what I want to do, though, is set a little bit of the sort of the background to radio, do a little bit of the history of it. I think that's appropriate so you can see what's going on. Maxwell, in 1864, came up with a theory of electromagnetism. Now, those of you who have ever studied will have loved Maxwell's equations. They were always fun. I can't say I ever really understood them, but somehow I survived the exam. Anyway, Maxwell was able to come up with the theory of electromagnetism, and that was the sort of the starting point. Right, then somewhat later, Heinrich Hertz did some experiments where he was actually able to transmit electromagnetic waves, in this case, radio waves, sort of proving Maxwell's theory. So we've had the theory, we've now got the very early demonstration that it actually is possible. So moving on from that, we start to get sort of a name you will know, Marconi. Okay, now I think it's fair to say Marconi was very, very good at taking other people's ideas, refining them, making them work, and doing self-promotion. So he wasn't necessarily an inventor, but he was extremely good at actually managing to turn it into something useful. And by 1895, 2 miles transmission, that's getting impressive. And
we've got a problem, the sound's not going out. Can you read?
okay, sorry, we had a comment the sound wasn't going out, but we actually have someone in the room monitoring the outgoing video and audio. I'm very grateful that we're doing that, because that tells us the problem must be whoever is trying to listen to this. So in 1901, signals from Poldhu to Newfoundland. That's slightly controversial whether that actually happened. However, I think we're going to have to accept it, it did. The systems are what's known as CW, continuous wave, Morse code, spark gap transmitters. You can't, with this technology, do voice. And what I'm going to do in a moment, I'll actually let you hear some spark transmission. This is what it sounded like. This is the sort of thing it was. So let's just try, hope it works. So what we've got there are sparks, maybe 10 sparks a second being turned on and off. So you end up with Morse code there. So that type of transmission is inherently very wideband, and you certainly can't do any form of what we would call amplitude modulation. Voice is not possible with that. However, if it'll jump forward, go on. Fessenden in 1906 used a particular alternator which allowed him to generate sine waves. Once you have a sine wave, you've got the possibility of altering the height of it, the amplitude, in sympathy with a voice. Then you're starting to be able to transmit voice signals. So he was the first one to achieve amplitude modulation. And I'm sorry, I'm pinching all these bits from Wikipedia. I don't make any great apology for it. It's a suitable resource for this. So you can see some great big rotary bits and pieces to produce the sine wave. Okay, so we're starting to get an idea of the transmission, but I want to, first of all, actually start to look at what receivers were being used. You know, how did the average person receive this? Well, the classic would have been a crystal set. The idea is, well, I've got a pointer here somewhere, but I can't find it. Got a pointer? Oh, is it on? Oh, thank you. Okay,
Sorry,
thank you. Got to go back. But, there we go. In a minute, I'm going to abandon it because I can't. There we go. What you've got is the aerial, a diode. Now that is the key part. D is the diode, which is the key element. That takes the varying height of the waveform. The varying height is being varied in sympathy with the voice. If you can clip off, take the voice, and using a diode, you can recover it, the capacitor to smooth things out, and some headphones. These bits, L and C1, are the tuning. So all you have is 4 components. You've got an inductor, L, a capacitor, C1, which you alter. The two together tune the receiver. The diode converts it back into audio, and the C2 and E, or C2 smooths it, and E are the headphones. The difficult bit was the diode. Now you can make a very basic diode using a material such as galena and a wire, and that's what we're looking at the top of the box you can see on the screen. So that's the old cat twister is what it would have been called. So it's just to produce a diode, because the diode, the rectifying part, is the awkward bit to build. They don't naturally occur. I think, oh goodness, sorry about that. As we go into the 1920s and radios become a consumer product, prior to that, they were experimental. They had to have a lot of money to do anything. The BBC being formed in 1922 with a specific mission, which as far as I know, I think it's still got, hasn't it? Inform, educate and entertain. I think that's still the basic mission. And the key element that allows it to become a consumer product was the development of the thermionic valve. Fleming, was it? Again, my memory is a bit vague on it, but the valve was then a diode. It was a diode that was repeatable in the sense of you weren't messing around with a little piece of wire on a piece of mineral attempting to produce a rectifying junction. You'd got the valve. So this led through to a number of possible approaches to actually produce a receiver. There's the tuned radio frequency. That's the one we looked at a moment ago. Just an inductor and a capacitor as a resonance circuit to pick out the signal you want. there's something called a regenerative. The basic idea there is to take part of the signal and feed it around through an amplifier repeatedly, and you get extra amplification because it's going through it over and over again. And then the other one is the superheterodyne, which is the one, as you'll see, that's the one that became mainstream. That's the one that became all conquering, I suppose, until we got into the, certainly in domestic terms, consumer terms, you'd have to be up to the 2000s before the superheterodyne was challenged as a way of doing things. So I think it's worth saying, what do we want a receiver to do? Because this will come through into what the development of the receiver. Well, it's got to select the signal. You've got an aerial piece of wire picking up lots and lots of signals across the waveband. You know, you can imagine in your mind the old tuning dial on a radio. They've got all those signals coming in at the same time. So you need to pick out the one you want. You've got to select it. Needs to amplify it. What comes down the aerial wire will be a very weak signal. It won't be strong enough for you to use. So you've got to somehow amplify it. You've then got to demodulate it. That's the diode. Demodulation is the term used for recovering the actual information, the speech, the TV, whatever it is you're transmitting. You've got to recover it. That shouldn't have jumped there. I don't think, or maybe it should. Sorry, I didn't think it was going to say that. Okay. Let's have a look at the tuned radio frequency receiver, because looking at this will give you a clue to what the issues are. The basic idea is that you've got two tuned amplifiers, or two or more. Their job is to pick out the signal and boost it at the same time. Then there's the demodulator to get the original signal back, and then there's another amplifier just to boost the original signal. So out of the demodulator, there might be the voice signal, and then that's to boost it up enough to feed headphones or to feed a loudspeaker. So let's get into it a little bit of theory, some math, but nothing too exciting. The tuned amplifier that uses a resonant circuit based on an inductor and capacitor. That's the L and the C on the bottom left. There's usually some resistance, you can't avoid it, so I'll put that in there. So if you put an inductor and a capacitor, and an inductor is a coil, I should say, all we're talking about is a coil of wire. That's all I mean by an inductor. A capacitor is two metal plates with a gap between them. Two together, and they are capable of picking out a signal using the formula many of you will be aware of, 1/2 pi root LC. L is the inductor in henries, C is a capacitance in farads. So assuming you can measure the inductance and the capacitance, you can calculate where it's going to resonate, and therefore you can tell what wanted signal you're going to pick up. Okay, so I did a plot. If you use a 2.5 microhenry, now the other thing to notice is, unfortunately, in this sort of engineering, you end up with very small numbers. So 2.5 microhenries is quite a lot, 2.5 times 10 to the minus 6 henries. Sadly, even worse, the capacitor is 100 picofarad, 100 times 10 to the minus 12. The numbers are very small, but hey, that's just the real world, and nothing we can do about that. If you do that and a 10,000 ohm resistor, what we get is, if you increase the frequency along the bottom axis, you can see at 10 megahertz, there's a peak. That is the selective effect of the inductance and the capacitance. If you start cascading the stages, and what I mean by that is you have one tuned amplifier that feeds another one, and you plot what's going on, you find that, oh goodness, I'm trying to put my finger on the right button. Sorry, lost it. Go forward again. There we go. You find that with two of them, you get you get a broader peak and steeper slopes. That's a single, the black one is a single tuned amplifier. The red one is a two-stage tuned amplifier. So putting two stages on is quite good. Steeper sides means it's going to be better at selecting what you want, and it's providing more amplification. So, hey, this sounds good. why don't we start having a few more? Rather than just 2 stages, why don't we have more? Because that will make it easier to pick out the signal and better amplification. So, reading that, if the process of cascading them to obtain the performance required is continued, then you need a lot of stages. Particularly true at HF, i.e. shortwave, 3 to 30 megahertz, where the bandwidth required is only a small percentage of the reception frequency. So to give you some numbers, for example, we may be having a transmitter or receiver at 15 megahertz, and we need it to be only perhaps 5 kilohertz wide. So 15 megahertz to 5 kilohertz is a ratio of what? 3,000 to 1, is it? I think it is, doing it quickly in my head. So, you know, it's only a very small percentage. So we're going to need quite a number of cascaded stages to get the performance. So let's have a look what I mean. There's a single stage. Those of you who are familiar with electronics will recognize this part here is base bias resistors, a transistor, emitter resistor with a bypass capacitor. And up the top, there the capacitors L1 and C1, they set the frequency. Yeah, all looks good. So what we'll do is we'll add another one on. That looks good. We've now got 2, one after another. This should make it easier to select what we want and give us more amplification. Well, we'll have a third one, shall we? Well, we can keep adding these on as often as we like, at least in principle. So it all looks fairly hopeful. So you're starting to look at circuits like that, but as I suspect you will anticipate, there's going to be a big but coming up. Okay, let's have a look at this. This is a practical, brackets, impractical receiver. The issue is, here, first 4 blocks are the tuned amplifiers. So each one has got a capacitor which we alter to tune and an inductor. So those 2, the capacitor and the inductor, they set channel you're trying to pick out. And we've got 4 of them. Okay, I think most of you here will be engineers. You will spot what the problem's going to be. How are you going to get all 4 of those to tune to exactly the same frequency all the time? You'll move the frequency and they won't quite all move by exactly the same amount. So the whole thing will fall apart. So that's the issue with the tuned radio frequency receiver. Getting everything to tune at the same time in parallel is going to be very difficult. To get them all to track is the terminology. Very occasionally, this can be a workable circuit. Any of you who over the years have had any sort of radio-controlled clock? Well, it only ever picks up one frequency, doesn't it? So you could do this, you'd set it up and it'd be fine, you'd never want to move it. And it would be possibly a relatively cheap way of doing it. However, most receivers, we need to tune to different frequencies. So that approach, although superficially okay, in practice is not okay. Happy with that logic? Okay, so where do we go from here? Well, we go to Edwin Armstrong. He is credited with inventing the superhet and actually inventing FM, frequency modulation as well. So quite a clever guy, an American. The basis of it, which I'm going to explain, is to take any signal, whatever it is you're trying to receive, you move it to a single fixed frequency. And I'll explain what I mean by that as we go on. All the amplification and selectivity is achieved at this, what's called intermediate frequency. Then you follow it with demodulation and amplification. But I'll show you what I mean by this. What's this idea of moving it to a different frequency? That's the key to it. Let's see if we can press the right button. Okay, so at first sight, it looks considerably more complicated. If we just think about it carefully, you've got 2 tuned amplifiers there, a bit like we had before. Yeah, we had tuned amplifiers. We've now stuck 3 extra bits on the front, an RF amplifier, a mixer, and an oscillator. The idea, which I'm going to explain, is that whatever the frequency it comes into the RF amplifier is, let's say, I don't know, 8 megahertz. The 8 megahertz, its amplitude's going up and down, it's carrying the information, it's carrying your voice. By the time it comes out here, it will be at another frequency. It'll still have the same voice information, but it might be at, let's say, 500 kilohertz. And this is the interesting bit. I said 8 megahertz. If we now wanted to receive 5 megahertz, by the time it reached the input to the IF amplifier, it would be 500 kilohertz again. Every time it is converted to the same frequency. And I'll go back to how this works in a moment. But because these are then on the same frequency all the time, there's no problem. They're going to behave themselves. We're not trying to vary them anymore. So, okay. Amplifier and filter provides gain and stops images. Again, I'll come back to what an image is. The image is the one clear issue with the superhead. The mixer and the oscillator, they move the incoming frequency to the frequency you want. So together they're called a frequency changer, because that's what they do. And the IF amplifiers, they do all the real work. They're the ones that pick out the signal, they boost it up, and feed it into the amplifier at the far end. So this, as I say, this from about the, yeah. I'm sorry, I don't have any control over
No,
that.
unfortunately, the system, I can move it to the bottom. Let's see if it's better at the bottom.
Well, you blank up that.
Yeah, I think that's at the top.
Okay, yeah, well,
Okay, sorry, just a minor technical issue. Okay.
no, by sticking it up there out the way.
Yeah.
Yeah, unfortunately, it's when the speaker moves.
Okay. Okay, so we've got the basis of it. I'll now talk you through how we actually go about doing this. I'm going to put a bit of theory in because I'm hoping most of you are engineers and you like maths. I say that tongue in cheek. Most engineers avoid maths except when it's actually some use to them. But now it won't go forward now you've done that. John, I think we're broken.
That's right.
Well, we got it. Okay, right, a little bit of theory now. A little bit of mathematics for those of you who love such things. Input 1 and input 2. I'm just going to go back briefly. I'm explaining this thing called the mixer. Okay, we're looking at the mixer now. This is what I'm concentrating on. So, mixer. All a mixer does is it's a multiplier. Okay, that's all its job is. We'll see how you could do a multiplier in a minute, but basically it multiplies two signals together. So we've got signal V1 sine omega 1t and V2 sine omega 2t. Basically two sine waves. If you feed two sine waves in to a mixer, what you get coming out, if you press the right button, go back, what you get coming out is a sum term and a difference term. So interpreting this bit to the right of the equals, what it says is, if you put in two sine waves at different frequencies, what you get out is the sum and the difference. So again, let's put some numbers in so we get a bit of a handle on what I mean. It means if you put in, let's say, 10 megahertz and 12 megahertz, you would get out first term 10 plus 12 is 22, and you get 10 minus 12, you get 2. So that's what's going to come out. And that's great trigonometric identity that you probably did at school when you did your O-levels. Trigonometric identity, sine A, sine B. Yeah. There you go. Yeah, so I'm not doing any magic here. This is fairly standard, straightforward stuff. But in this case, it's got some real practical, useful implications. So and then I've got some numbers here. If we use 10 megahertz and 9, you get 455. If you use 12 and 11, 545, you get 455. Now, the significant bit is, if you notice, the output on the right-hand side is exactly the same, 455, but the signal we're trying to receive, 10, and the signal we're trying to receive, 12, are different. So, by fiddling with F2, frequency 2, we have been able to convert the frequency incoming 10 and 12, both to 455. And that's straightforward mathematics, trying to apply it in a useful way. So the bottom line, by changing frequency 2, then frequency 1 can be converted to a single specific frequency. That's the frequency changer, which is the core of the super heterodyne receiver. If this didn't exist, the super het isn't practical, or doesn't exist. Right, so how can we actually do it? How do you multiply two signals together? Okay, any device with a square law characteristic can be used. This is perhaps going slightly a bit mathematical, but if you look at the equation for a diode, a semiconductor diode, it looks like that. It's got, oh goodness, I keep pressing the wrong button. Sorry about that. So, okay, so I think I will control. The two buttons are close together though. But now it won't work. Oh goodness, it's now gone backwards. Sorry about this, everybody. Right, hang on. Go back, go back, go. Sorry, I apologise. It's I just want to keep going back several stages. Keep going. That's it. 2, I think. Go on.
Going backwards is all.
Yes. I'm sorry. It doesn't seem to want to go back. Here we go. Okay, this is it. So a diode has that equation. All we are going to do, well, the key bit about that is the fact that it has got a square. This is an exponential term, but again, going back to mathematics, the exponential term, you can actually expand it as a power series. And the key one we're interested in for the moment is the x squared term. All this means is that will do the work of a multiplier. So let's see if we can turn that into a bit more. Just thinking of that term, forget the others. The other terms exist, but they're not of interest to us. They're not going to help what we're trying to do. So what it says is, again, some straightforward maths. 1 plus the other, square them, gives you 1, 2, 1 times the other times 2, one of them squared, the other one squared. Right, there's a multiplication term. They're the two frequencies multiplied together, just what we need to make a super heterodyne work. There will be other frequencies coming out, but we're not too bothered about those for what we're doing. So, 2, W1, omega 1, omega 2 is the key one. The other terms are not important. Conclusion, a diode or other rectifying junction will act as a multiplier. That's the bottom line, which is something that happens in practice, but it's good to see there's a bit of math behind it. We're not just sort of guessing and hoping it works. There is some theory there. Okay. Oh, now I'm afraid I'm having a little technical trouble here. I pressed the button, nothing happens. I pressed it again and I've lost everything. Okay, can we go forward? Oh, good. Thank you. Okay, now the super het works very well, but it's got one inherent bug or problem with it. Let's see if we can identify that, because again, it says something about the design you're going to need. Multiply the two together, we get 1 plus the other, 1 minus the other. We've talked about that. Okay, so some numbers in. If we're trying to receive 10 megahertz, we need the other frequency at 9.545. The difference is 455. Everything looks good. That's doing what we need it to. Sadly, as well as 10, if there happens to also be coming down the aerial 9.09, when you put that along with 9.545, which we're already using, you still get 455. So sadly, there are two frequencies, both of which will give 455, because the way to think of this is it produces the sum and the difference. So how can I put it? 5 minus 3 gives 2, 3 minus 5 gives minus 2, but it still gives 2. So that's the problem. It's the sum and the difference. So we're going to have to somehow, on our design, make sure that the 9.09 is removed. We don't want it. It will be interference. It will stop the receiver behaving itself. And that is going to be reflected in the design. Right, am I pressing the right button? Yeah, I'm pressing it. It's not doing it. I'm sorry about the technical issues here. Normally I prod it with the finger and that does it. Yeah, fine, that's fine. Okay, the the solution to this then is to have this RF amplifier stroke filter. Remember, the problem is coming out of the mixer. That's the multiplier. That's the thing that's turning out these unwanted frequencies. So what we need to do is only let through frequency we want. So this filter here, its job is to let through the frequency you're trying to receive, but stop the one you don't want. And the one that you don't want is called the image. So we've now got the basis of a viable receiver. That will work. It does work. It's perfectly achievable, and it was in use from the 1930s onwards. So it's a perfectly good workable receiver. I can't think what's coming up next. Give me a moment to have a look. Okay, right. So, right. Okay. So now let's start moving on to what I feel like was the topic. We've got to make some definitions. Amateurs always used to make their own radios. From about the 50s onwards, people started buying them. So I'm looking at commercially made ones, and I'm talking about a transceiver, right? Let's understand what I mean by that. A radio, you could have a system which is what would have been used on ships, etc., certainly in the 40s, 50s, and 60s. You had a transmitter and you had a receiver, and the aerial switched between them depending on whether you were transmitting or receiving. Okay, perfectly sensible. However, what I'm looking at is where the transmitter and the receiver are integrated and share system components. As we'll see on this one later on, when I show you the diagram, you'll see that a lot of the parts or the functional blocks that are used in it are used by both the transmitter and the receiver. So we don't need two complete sets of parts. We can just switch them carefully and end up using the same part for both jobs. I'm going to talk about all solid state. During the development of the transceiver, there was a phase when most of the circuitry would be done with transistors, but high power transmitting transistors were both expensive and very delicate. So you would have a valve for the main transmitter output that did all the work. That's called a hybrid. I'm not going to consider that. And I'm going to look at 100 watts output. That became the sort of the de facto standard. I don't actually know why, but I suspect it would have been US and Japanese licensing allied with the transistors that could be produced at a reasonable cost. But it became the norm. I don't actually know exactly why, and I'm quite happy for somebody to argue with me about that. They can argue with me about anything, actually, I don't mind. Okay, so 1960s. We've got at the top there I think it's a KW2000, which is a British-made transceiver, and then we've got a Swan 350 in the bottom right, which was an American-made one. At this point, nothing Japanese. They were European or American very largely. However, right, this is where we start getting onto some of the constructional stuff. You can see what it's like underneath. Yeah, okay. The basic approach was to have a series of valves and string components off the valve where they plugged in. I'm sorry, those of you online won't be able to see that, but I think that'll be a valve base with components off it. I'm trying to see some more. Can't see any more, but that's, and then you would have a big bundle of wires running around. They are not going to be easy to produce. They're not going to be cheap to produce by the very nature of the construction. Right. Hybrid radios. This is where we move from an all valve radio to an all transistor. The absolute classic, which is where the Japanese basically conquered the market, was the FT101. Now, it may mean something to some of you, it won't to others. However, I think it's fair to say that was the beginning of the Japanese conquest. Right. What have we got inside? First of all, it looks a lot neater. The top left picture is the top view. The bottom right is the bottom view. It's a lot nicer inside, very well engineered in a mechanical sense of engineering. Right. It was a hybrid, and I'm sort of doing this as part of the scene setting. It's not what the main talk is about. It used the printed circuit boards. It wasn't all components strung from point to point, which we saw on the earlier one. And then it started to have things which were really, well, this is why it started to take over. It could be 240 volts, or you could run it on 12 volts. Now, that would have been a revelation, something running on 12 volts. I have seen people with these in their cars. Yeah, okay. Not my idea. 14 kilograms, absolutely huge. It sort of sat half under the dashboard in the way of the gear lever. It was not an ideal arrangement, but it was workable because it was 12 volts. Right, we now start to get on to the ones I'm talking about. The Atlas 180, 1973. So we have an Atlas 180. Okay, so we're looking at a radio now that, whatever it is, 50 years old? Yeah, 50 years old. That's still completely working. It's in good condition. There's nothing wrong with it. That's an advert probably taken from the American magazine. But what I've tried to do is put the 2024 prices on. I went and found one of these calculate the inflation calculators. So you can see you're not looking at exactly a bargain, are you? They were expensive. I'm just trying to set the scene. So you're looking at a £3,000 radio. However, it was based on military designs, the name of which I've forgotten for the moment, and it was state of the art. When you saw the pictures a minute ago of the 1960s transceivers, what was that other one? How many? 14 kilograms? I'm picking that up with one hand at the moment, and look at the size of it. It's small, it's compact, certainly not perfect, but it was a step forward. It really was a groundbreaker. It was straightforward. It used single conversion. I'll come back to that later, both on transmit and receive, and had a variable frequency oscillator whose frequency changed for each band. You've got to tune it. The sort of, what I've taught you so far is the idea of varying capacitor, which to change the resonant frequency of a circuit to change the frequency. That is all you have got on that. That's all it is. Now that you might say, well, okay, fair enough. But there are some significant downsides. Yes, it's small, it works, but it certainly isn't perfect. Okay, let's look at the insides. This is the block diagram of it. And I think you should start to recognize it as a superheterodyne. We've got, at the beginning, we've got filters. Those are to stop the images. We said you needed those. We've got some more filters there. This is the multiplier we talked about. There's the oscillator, one signal going in, the other signal coming in from the aerial. Multiply them, amplify them, now at a fixed frequency of 5520 kilohertz. A crystal filter. Crystal filter is a particular type of filter based on quartz crystals. The point about a quartz crystal is you can get a very, very selective filter. That's the point about it. They're made out of taking a slice of quartz and getting exactly the right thickness and putting it between two metal plates, and it will resonate on a very, very accurate frequency. I'm trying to think it's not magnetostrictive anyway. It's an effect. So it would then go through the filter, which will chop off everything except 5520, boost it up. This bit and this another multiplier. I'm not going to go into the detail of it, but that is the demodulator. That's the equivalent of the diode. That's the bit that recovers the signal, and then it goes through an audio amplifier and out to the speaker. That's the transmit strip. Fundamentally, it is just a superhead. That's all it is, but it's what's called single conversion. Transmitter. I'm not going to go into it too much, other than to point out a few things. Whoa, done it again. Captain the wrong one. If you notice, on the receive, we've got two mixers, an oscillator, some amplifiers, and a filter. Transmitter, two mixers, an oscillator, filter, amplifier. So we've got the same parts in both the transmitter and the receiver. So we don't need to have inside the box, we don't need all the top part and all the bottom part separately. All we do is reuse the parts and switch them to make them do different jobs between transmit and receive. That way it's economical, keeps the power usage down, and generally a neat way to do it. This has come out of the Atlas's manual, which shows, okay, it sort of shows the way they're all switched. I have no intention of trying to explain it, but it is showing the switching. So this is a transceiver, the idea of shared parts between the two sides. The SSB, single sideband, again, I won't go into it. It's a particular type of transmission that's pretty much universally used by amateurs. Having said that, it's also used by the military. Aircraft, once they're out of range of land, will be using single sideband signals on shortwave. So if you're going over the pole or something, you'll be using SSB. So very widely used. It's a particularly efficient mode of transmission. Okay, so let's have a look at, whilst this Atlas is perfectly viable, what makes it less than perfect? Because it's only if you know what's less than perfect, you can start to figure out what you're going to do about it to get nearer to perfection. Okay, the way it works is on these frequency bands, or to say these frequencies, the transmitted frequency, the oscillator has to go on the transmitted frequency, so it might be 7 plus 5.52. So the oscillator, the main resonant one, is running at 12 megahertz. Okay, that's just the way they've done it. And for, oh, done it again. I keep pressing the wrong button. They're next to each other. Sorry. On 14 megahertz, you have to take off 5.52. Right. The problem is the stability of the oscillator. If we have got the oscillator on 7 megahertz, 7 plus 5.52, if it's running at 12 megahertz, okay, trying to get an oscillator stable that won't change frequency with time. For example, one of the issues, and it sounds unlikely, the inductor is made up of a coil of wire on a coil form or something to support it. Slight changes in temperature, the coil former will very slightly increase in diameter, which will very slightly increase the inductor, the value of the inductor, which will cause the frequency to change. And the issue becomes the very nature of single sideband transmission. Any change of more than about 100 hertz would be audible. It would be an issue. So you're trying to get something running at 12,000 hertz, 12 million hertz, accurate to within 100 and stay there. Okay, that's going to be a challenge. That's going to be difficult to achieve. The main way around it was to use high quality components. That would help, but the fact that you had on the front here, you probably can't see it, but there's whatever it is, there's a band knob. You can hear it, a big crunchy knob with switches going through the radio. By definition, the contacts are going to get dirty, so it isn't going to be perfect. So it worked, it was a groundbreaker, but it certainly isn't perfect. It's got issues with it. But when you are otherwise going to be having one of those FT101s, which is the same power rating, but is it 13 kilograms, etc., it still look pretty good. Okay, this actually isn't inside of mine, that's a friend of mine's, which is somewhat muddled up. But that's the basic idea with the top off. It's a little hard to see what's going on, but we've got circuit board there. I think that's a circuit board. The circuit board's there, and they all plug in. This curved bit is, though you can't, again, I'll show you later, but I can do it. When you turn this, what you're looking at is the dial. That curved bit is the dial, which is sort of doing that. So that's giving you the frequency readout. The power transistors that did all the work were mounted on this great big black heatsink on the back. Was somewhat delicate. It was quite easy to blow them up. Okay, you know, if you're a manufacturer, you're going to push those transistors to the limit because the specification sounds great. Sadly, if they weren't treated with respect, they would fail. The other one was a bit of a problem. If you look at this, the heat sink on the back, hold of it again. The heat sink on the back is what's called convection cooling, those fins. So it's the heat, that's just to get rid of the heat. You're relying on an airflow over those, which would be difficult to achieve if you mounted it in some sort of a close environment. So good, but not perfect. These are all radios I have. So that's the Atlas 180. Another competitor would have been Swan. Swan was that great big one we saw with all the components all over the bottom of it. They moved on. And this would have been, well, about £2,500 in 1978. I haven't brought it with me. What they did, to get over some of the problems of stability, was to start using some crystals. The trick then is we have the variable oscillator always working over exactly the same frequency range. It never changes. Okay, as engineers, if you can do something over a limited range all the time, you're going to be able to do a much better job than if you're trying to switch it to do different things all the time. So what they did was to use the same variable frequency oscillator all the time. So it used an oscillator on 5 to 5.5 megahertz. Interestingly, this was with what's called permeability tuning. Think back to the circuit. You remember we had an inductor and a capacitor in parallel? Either one you could change to alter the resonant frequency. The Atlas I just showed you, you changed the capacitor. This changed the inductor. It wound a slug of ferrite into the inductor, which changes the inductor value. Apparently, it's easier to get a linear response, and it tends to be more stable. But this is where they're both American manufacturers, and they're fighting it out to see who could produce the cleverest radio. So I won't spend too long on this. We're slightly getting off into the big detail, but for 14 megahertz, what you would do is take the 5.5 megahertz of the variable oscillator, multiply it with 28.5, and if you remember, you've got the sum and you've got the difference, and the difference is 23. So the 5.5 will vary, that's fixed, so the 23 will now vary in sympathy as you turn the knob on the variable oscillator. And then what you do is the 23 is then multiplied with the single sideband signal. So they're trying to run the variable oscillator always on the same frequency range. That's the key to it. So therefore you can do a much better job. But of course, you don't get something for nothing. It's more complicated, which may or may not be a problem. Okay, I won't talk too much about it, but there's the crystal. Multiply them by the variable oscillator, and the output comes out where you want it. Right, inside, this is one. If I took the lid off the top of mine, you can start to see a little bit more what we're dealing with here. Can you see the, I don't know, what color would you call that? Whitey, cadmium plated sort of color box. That is the variable oscillator. So, and that shaft coming out of it is the bronze shaft goes to the knob on the front. This is a variable capacitor down in the bottom right on the left-hand one. And that is for peaking up the signal. It's the filter at the front of the receiver to pick out the signal you want and chuck away the images. And then we've got that square block on the top circuit board on the left-hand side. That's the filter, that's the quartz filter. But what we've got is 1, 2, 3 boards on the top. 1, 2, 3, 4, 5, at least 5 boards on the top. There's a lot of circuit boards and wiring between them. I have my suspicions, though I mean, clearly I don't know, that what was happening is a board would be designed to do a function, like a filter, and then it would be used in different radios, so you didn't have to keep redesigning the circuit board. So you'd have a different combination of circuit boards in a different radio to achieve what you were trying to achieve. Okay, this is another one of mine sitting at home. And this would have been pretty much top of the range in its time. We're looking at a £3,000 radio from 1981. And this is starting to make some more jumps in technology. We've gone from the Atlas, where everything relied on an oscillator, through to the one we just looked at, which was more stable because it had got some crystals in and the oscillator was always over the same range. This one, instead of using quartz crystals for what we call the band oscillators, it was now using a synthesizer. Right, again, I'm not going to go into the design of synthesizers, but they allow you to get a range of frequencies which are very stable based on one single crystal. So all you need is one really good crystal and you can generate a whole range of frequencies. Don't worry about that PTO business. Then you've still got a great big band switch. Bottom right-hand corner, there's a big clunky switch, and there's a great big bar that goes right the way from the front of the radio to the back, with switches on several places down it, which is okay, but it's a source of failure. Inevitably, something with clunking switches, probably mounted on something like Paxilin, which is not the most robust of stuff, will eventually fail. Mine is still working, thank goodness. Have a look inside again. This is by a company called Cubic, who took over Swan. And we've got, again, circuit, top view, circuit board on the left. Look, judging by the fact you've got 33333, those will be the filters for each of the bands. These are the ones to pick out the wanted signals and forget the rest. So we've got those. So crystal filters. Nothing particularly remarkable. I do not have one of these, but this was a step forward in the amateur market. It's something called double conversion. This is not to pretend that double conversion hadn't been done before. There was a classic receiver called a Raycol RA17 from the late 1950s, which used double conversion, but it had got valve all over the place. It was a very heavy radio, real military grade, very impressive piece of kit. But this is the first one I've been able to pin down of an amateur one. This was available as a kit. I don't think they sold that many, because how many people want to spend £2,500 on a kit and then discover they put it together wrongly? It's probably not a great plan. Okay, double conversion. This is a bit weird. If you remember, a superhet, the idea is to convert all the incoming channels, whatever it is you want to receive, to one single frequency. This, first of all, it goes in and goes through the first multiplier, the first mixer, and it's changed to one frequency, and we do a bit of filtering. It then is changed in frequency again, goes through a filter, and then we recover the signal. So its frequency is changed twice, which at first sight seems like an unnecessary complication and a recipe for trouble. But there are reasons for doing it. The main one is that the first, I'm using the values that were used in this, the first intermediate frequency, the first IF of 8.65 is relatively high, the second is relatively low. The first one, the idea is, and I'm not going to go back and try and establish this, but if you have first one, the one here, the one there, if it's fairly high in frequency, it's very good or relatively easy to get rid of the unwanted signals. Whereas the lower one is much easier then to pick out the signals you want and amplify them. So there are reasons for doing it. I think we'll ignore that because it's just a bit of a complicated diagram. Okay, perhaps this is more helpful. This is the sort of how we're trying to do it. In fact, I think that diagram, I'm fairly sure, if I remember rightly, is the, how can I pick this up? Is that, okay, that's what we're looking at. This is an Icom 735 from the mid-80s. So the signals come in, and anywhere between 1 and 30, we do some filtering, and then we up convert them. Now that is a bit weird. So far, we've been talking about the incoming frequency being made lower than we amplify, but this is doing exactly the opposite. It's going up in frequency, which at first sight seems very strange. And then once we've done some filtering, we'll then bring it back down to a low frequency. The advantage of doing this, again, without spending too much time on it, we can then have a receiver that goes all the way between 1 and 30 megahertz in one go. You haven't got any switching, you haven't got any filter issues. It allows you to have what's called a general coverage receiver, rather than one that only does small chunks. It might do a 500 kilohertz chunk at several places. This can do any frequency you like. This was done by the Rakel RA17 in the 50s. Okay, so Drake TR7. Again, I have one of those at home, and I've just been making, see that's the external VFO. It has some end cheeks, the ones there. I've just been 3D printing those, but they were missing. Anyway, that's beside the point. Drake were making receivers, and they were transmitted and very well thought of. And this was their last mainstream one before the Japanese wiped them out. The clever bit here is it's partly synthesized. The only thing that is a free-running oscillator is the main oscillator, which is on 5 megahertz. It uses up conversion, general coverage, transmit and receive. And for those of you who are amateurs, you will know what WARC 79 was. It was when amateurs were allocated a whole load of new bands, new wave bands, in other words, new frequencies. The problem was all the older pieces of equipment only had set frequencies, and oh dear, we've suddenly got all these new frequencies and we can't use them. We can't modify the radio. Whereas this, because it's a general coverage, you could use them. So it gave it an immediate commercial advantage. Lots of plug-in boards. It's an absolute nightmare to work on, as I've found, because everything is on a board that's plugged in down a little hole where you can't see what's going on the circuit board. So therefore, you can't fix it. Of course, during production, they'd have had it on some sort of a jig where they could work on the boards to get them to behave themselves. So that's the TR7. And then each, as you can see, there's the inside. Each one of those is a circuit board. There's a lot of circuit boards in there. There's an awful lot of stuff in there. But they made it work. In fact, it's actually worse than that, because the digital display on the front panel is driven by another board that actually sits over the top of all those. So I had a problem with mine recently, and it was a bit of a devil to find. And then I discovered it was operator error. I was doing something stupid, and eventually there wasn't anything wrong with it. It was just what I was doing. So we're looking at the construction a little bit. That one is significant because it's up conversion. This one is, I believe, is another one that was a sort of a bit of a groundbreaker. It has no free-running oscillators at all. It is totally based on synthesized. It's not easy to tune. It's very weird. I think most of you would be used to the idea of, you know, you turn the knob one way, you turn the knob the other way to tune up and down. I think we're all used to that sort of thing. This one, the big knob in the middle, you turn it a bit to the right and it starts tuning up, turn it back to the middle, it stops. Turn it to the left and it starts tuning down, turn it to the center and it stops. So you spend your time going backwards and forwards attempting to tune something in. It's a nightmare. However, it had some other positives. For the first time ever, you could have, as you can see on the microphone, you could have an up and a down button. So if you're using it in your car, you just press the buttons on the microphone to tune it up and down. So although I would have said it was quite difficult to use, it did bring in some innovations that weren't there otherwise. It's interesting to realize it was based on an Astro 2000 by CAR, whoever they were, but at 3,600 for the thing in the bottom right corner. You know, that was never going to sell well, was it? It was a lot of money. But this is a direct descendant of it. If we start looking inside, you can see how the circuit techniques are starting to change. Can you see we've now got one huge board? We're not onto lots of little boards. We're starting to get to a single circuit board, which is going to improve reliability. You haven't got to have cables all over the place. The other thing which is significant, the front panel controls are on a circuit board, and they just sort of poke through the front panel. you can imagine what I mean, as opposed to the controls actually being mounted on the front panel. So this would make servicing and assembly that much easier, because you're not having to, in the workshop, you're not having to mount things directly through the front panel. They're all on that circuit board there. So construction-wise, it is moving on substantially. And then the one we've got down here, right, it's interesting to note, this is 1985. Let's just go back one, another one. Okay, so this is 2,100 in current prices. This is 1,900, so it's cheaper, but it's everything we've had before in one box. This is why the Japanese started to take over the market. They were technically better, and they were very competitively priced. So it's triple conversion, certainly on frequency, on FM it is. It's got up conversion, it's got general coverage, it's synthesized. And the other thing is, it no longer has that great big switch with a long bar going right the way through, all completely electronic. This was the first radio I had where you could actually control it remotely. You could send it data and it would tune itself to a different frequency. And you can only do that once you start to have completely electronic band switching. You're no longer relying on somebody manually switching things. The other thing which in construction I think is interesting, rather than the massive great heat sink on the Atlas, which you're relying on having enough air around, it just has a single massive die-cast heat sink, and that is a blower. So rather than air having to drift past it, you actually force air past it to keep it cool. Again, it doesn't look quite as homemade as some of the others. I mean, that won't have been cheap to do a die casting. It feels like the Japanese were very good at investing longer term to do it properly. Sorry, I've gone backwards. And if you open the lid, then that's the die cast bit. One massive circuit board. Where there's another picture. Oh, okay. So that's, if you like, gone through the radios. This is a video I did. That's this radio here.
Anyway,
you want to jump this filter halfway through where we look at the construction? You can do that. I think what we'll do is jump through the video where the lid's off it. That's probably what. Don't worry. Please forgive us while
controls up on.
Yeah, please forgive us while we fiddle with it. If we can't do it, we'll have to just. It's the next one.
Can you see the video?
No. Okay, well, look, we won't worry too much. Well, that's better.
This is the Cubic Astro 102 BXA. It's actually, of course, a Swan. In fact, it still says Swan here. Swan being ultimately a division of Astro. I think it's a particularly ugly radio. However, it does have some things which hadn't been on other radios. So let's just put it on. Okay. Somebody on there. Let's just have a look at a few things we've got here. So we've got IF gain and AGC, so continuous AGC adjustment.
Forward, purely because unless you're into radio, you're going to find that fairly tedious. This one I will show you. This is the one where the tuning is an absolute nightmare. So just see how, I think I demonstrate it.
This is the Swan Astro 150 SSB transceiver. There's also an Astro 151, which rather than covering 10 meters covers 160. Apart from that, they're the same. This was the radio that introduced to the mass market a completely synthesized oscillator. I'll turn it on in a moment and you'll see the main issue, certainly in terms of using it, and it's just not very usable. So let me turn it on. By the way, standby position is used if you want the memories to hold up, which we're not using at the moment. Anyway, put them on and you'll notice it's on 40 meters. However, it's going to take a second or two before the synthesizer goes into lock. That's what we're looking at the moment. Okay, it's in lock now. Now, what I will do is I'll tune it. Now, this is the bit that's a bit weird. The tuning knob here, you don't rotate it. You just move it one way to go down the band, move it the other way to go up. It is not easy to use, and I'm sure this didn't contribute to the sales of this. Anyway, let me go down the band and I'll show you what I mean. No, it's just tuning. Right, I'm going to try another one. Now that took a little time for me to actually be able to tune it in.
You get the idea. It wasn't easy to use. And then finally, the radio we've got here. I'll just play a little bit because I think we're pretty much getting out of time. So
let's have a look at the IC735's construction, because it's a good example of where construction techniques ended up by the mid-80s. For example, we've got moulded plastic front panel, no sheet metal with holes in it. Die cast heat sink, that's the blower with force air cooling, so the PA is on the other side of this, which obviously keeps the size down. I've taken the screws out already, so let's just lift it open. And we can see one or two other things that are fairly clear. We're back to, or we have a single large circuit board rather than multiple small boards. And also the connectors are all mounted directly onto the PCB and then are accessible through holes. So no need on the chassis to mount all the connectors. That's going to speed up production. If you need to do a board change, board out, board back in, reconnect, and it's done. No need for soldering and unsoldering. Good example of a nice compact HF rig from
could take any questions. If any come in online, happy to take those as well.
The chap that invented the superhet came first. Was it the mathematics bit, or was the actual?
I suspect, I don't know, but I'm guessing that the individual parts like the mixer, the oscillator and so on existed, and he put them together and found he could do it.
Right.
And then you could establish with the maths why it actually worked. Yeah. I just put the maths in because I thought when I was a student I couldn't figure out how you could multiply two signals together.
Any other question?
No,
Yeah, okay. Okay.
Just an observation, Bob. It seemed interesting that towards the end, particularly the Japanese were learning very much from computer construction, and that basically you were moving towards the same type of circuit boards as in computers.
Were the early double conversion radios Wadley loop?
No.
No, Heathkit used it as well in the 302. Heathkit used it in the 302. I think.
Okay.
Questions on that?
Just doing the lines, most of us remember the TV turret tuner, which had a fine tuning section to improve the image. Same stability issue. That was obviously about the thing. Yeah.
Development from there on to what's been the big.
I would think in terms of from there to people's thought, but it seemed to be refinements of the superhet and this, and then digital signal processing came in around 2000, allowing you gradually to move to a radio where everything was done digitally. I mean, that's just my opinion, but I think they started off with a superhead with digital signal processing on the back end and gradually moved over to 100% DSP.
If you look at the three technologies, Japanese, European, and American, which one was the most advanced? In my experience, American was always sort of a few years behind, but
my suspicion is Americans, by the nature of America, it was all focused on money. So therefore, you take something that's proven and you try and make money out of it. Whereas I think the Japanese were very good, as they did with cars, at taking ideas and doing them very, very well with a long-term horizon for investment. So therefore, it was done very carefully. But in many ways, Europe did a lot of the development work. So that would be my view, but I can't back that up with any facts.
The connectors the same on these radios, Bob, as they are on the modern radios. Did that design change?
Same, but we've moved over to ribbon cables, going into a ribbon cable socket on modern radios, which I don't like because I'm always worried when you take it out, how many times can you put it back in without wrecking it? So I'm a bit cautious of those. Yeah.
Okay. Good. Any more online, John? Any questions more questions? Well, thank you, Bob, for that great talk. Thank you. Thank you. David's going to say a vote of thanks. Is that right, David?
Yeah. Excuse me. Thank you, Bob. It was a talk that I don't know anything at all about. It's completely the wrong discipline. But I think you provided a sort of level of understanding that where we can pick up the basics. The mathematics wasn't too daunting, but it was very interesting to see the way in which the Europeans, the Americans, and in particular the Japanese took the technology to, sort of much better designs and much better functionality. It's obviously a very specialized area of interest that you've found absorbing over many, many years, and your enthusiasm has obviously come through in the presentation. So I think that I'll ask the people here in the face-to-face meeting and also the guys and girls on Zoom to give you again a good vote of thanks.
Thank you.
Thank you.
I think I've just gone through my radio back today. But I think it made it absolutely clear to me now what a superhead is and what the differences are between transceivers and receivers and transmitters.
I certainly, when I was learning about
Great.
thinking about receiving, I thought, superhead, what a complicated way to do anything. What's the point?
Yeah.
It's only when you start to see why you need to do that it makes any sense.
That's right. Yeah. Yeah.
But everybody, for those online, look forward to seeing you all on the 27th of October when Phil Judkin is doing New Maps Out from Hell. This is looking at the first generation of maritime drone warfare.
Good.
It's going to be interesting.
Yeah.
I've heard Phil's told me a little bit about what he's going to say, but I'm not saying anything. It's going to be good.
Thanks, Bob.
Thanks, everybody.
Thank you. Very good.
Yeah. Not taking the top. Absolutely. Now you've got to better be able to see why. Yeah, absolutely.
yes, basically says it's just things of the